I'm Mark Larson from Makino. We build machine tools, but we also have an R&D group that does a lot of research, so I'm here to just talk a little bit about that. One of the things you need to take away from this presentation is that if you're an engineer like I am, and you get an email from your marketing manager, and he says, hey, we need some ideas on what you can talk about at AeroDef, don't give him too many ideas. So I sent back an email and I said, well, I could talk about horsepower, I can talk about torque, I could talk about hard metals or cutting strategies, and it all ended up in my title. So I'm going to narrow that down for you and not talk about all those things because we'd be here forever. But I am going to talk about one particular item and then we'll bring it back home. So to begin with, why are we even talking about hard metals at all? And that's because composites still, in a lot of cases, have to be attached to titanium because of the CTE, right? Coefficient of thermal expansion. Also, aluminum is used in a lot of cases in aerospace, but in many cases, you still have to have the strength of a hard metal for landing gear, for other components of the aero structure. So a couple of reasons there that we're talking about this. All right, so we normally want to go fast, right? Everybody would love to have a yellow Lamborghini, right? Go fast, corner fast, speed up, you can drift in the corners and all that type of stuff. Or even better yet, Indy 500, you're on a track, no real sharp turns, just keep going fast all the time. But what if you have something you really want to take a lot of material and move it fast and move it well and get rid of it? It takes a lot of power. In some cases, you may have one big lump of something you want to move. So we have these other pieces of equipment for those types of applications. So the question is, you can either go fast or you can move more material, right? That's normally what we look at. Well, power consumption alone is something we see all the time from our customers, and it's not the best metric in a machine tool. So everyone wants a car to have lots of power, right? You step on the gas, you take off. But there's still transmission of power to the wheels that has to take place. There's that torque aspect, so we'll talk a little bit about that. So it isn't just power that's required for hard metals. All right, so a little background. Our team, like I said, we work for a machine tool builder, but we do a lot of R&D. Like, what kind of R&D? The machines are designed and built in Japan, but we do process R&D. So we look at tooling, we look at fixturing, we look at different programming packages, we look at evaluations of those packages and cutting forces. We do a lot of investigation into the process, how it's applied to the machine. So we have our team, we have equipment and software, and then I'm going to share some of the results that we've seen. In our team, we have 6 members, everything from a BS to MS to a PhD level, and we do a lot of different things with those. Multinational, Chinese, Mexicans, Japanese, US citizens, over 100 years of machining experience just looking at how metal is cut and what tools work. We're familiar with CAD/CAM systems. We have a lot of different ones that we utilize, and we look at GD&T, stats, all the things that go into a manufacturing process. We're located in Mason, Ohio, just north of Cincinnati. We have one area in the back of the building where we have a whole bunch of things to play with. So we have a T2, Makino T2, which is a 6-axis machine. We have a T1 that's a 5-axis machine, 81M that's 5-axis and 4-axis, and a couple of others to play around with. And then we also have a laser microjet, which probably would have been a better machine to talk about at this conference, but maybe next time. As far as software, we use a lot of CAD/CAM, SolidWorks, and CAD for 2D, 3D modeling, but CATIA, NX, Vericut, all the typicals. We like to use Vericut for simulation, and I know they're here, CG Tech is here. They have their Force that they've implemented in Vericut, which is something that I'm going to emphasize in this. Also, Third Wave Systems has production module, which allows you to also look at the force required in a cut. Both very important. So we do a lot of data collection. We do collection through some software from Fanuc called ServoGuide. What Fanuc's ServoGuide does is allows us to look at the control and see what is the control telling the servo to do and what did the servo just do when it comes back with that feedback. So we can track exactly what's going on with the machine that way. We have MetalMax for tap testing. So if you're doing high-speed aluminum machining, you want to know what the natural frequency of your tool is and you want to try and match that. For hard metals, we still want to know what the natural frequency is, but the stability lobes, if you know what I'm talking about, on this graph that's shown, are going to be very tight on a hard metal. So it's going to be hard to target an actual RPM to work with. But we do that, data collection. We have a Kistler dynamometer, which allows us to take actual force readings. So while we have the part on our fixture and we're taking measurements of whatever force we're applying to that part with the tool. We also have a Keyence microscope so we can take pictures, and then we do our own proprietary software as well. We have Makino software that was developed in Japan. We have local software our group has developed as well. So a lot of different things to work with. The results I'm going to show you today came from our T4 machine that we had in our shop for a number of years. We sold it to a customer, so it's gone now. But it had 134 horsepower spindle, lots of power. It had 787 foot-pounds of torque. So it was very well suited for hard metal machining. It was a purpose-built machine for hard metal. Same thing with our T2, which we still do have. Same spindle, basically, as the T4. So some of the results are from the T2. Some of the results are from the T4. They both have very high pressure and high flow rate coolant. And again, coolant's also very important in the hard metal machining aspect. So what's holding us back? Mostly forces, right? What's holding you in your chair? Gravitational force. When we look at a machine tool in cut, we have rotational forces, we have axial forces, spindle bearing loads, and tool bending moment. And we're going to talk a little bit about all those. And then once you have a force, if it's being operated at some length, an arm, you're going to end up with torque. And then lastly, we'll look at a little bit power, the thing I talked about first, right? So for hard metals, just to kind of give this a bracket here, we're talking about testing we've done in the different pH stainlesses, Carpenter, as well as titanium and some Inconel. So those would be what we would say hard metal type testing. And also, hard metals are typically going to be high strength. They're going to have high hardness in some cases. Some cases they're going to be heat resistant, the heat resistant superalloys. And some just have enough elasticity to be a real pain in the butt. The real problem, though, is force. So we're going to start there. So we have forces on the machine axes. Okay, so you have an X, Y, Z servo axis motor that's going to be loaded up based on how much material we're removing, how deep your cut is, those types of things. You're going to have forces on the tool and spindle, which are going to be your radial forces. Those forces applied to the spindle bearings are what resist the cutting force action as the cutter is going through the material. So in that case, we have about 3 different types. We have tangential that are perpendicular to the edge as the tool goes through the part. We have resultant force that may not be exactly perpendicular to anything, and then you have some XY components going on. And that's another place where we see some people get into trouble because they think because they're cutting in one direction, all the force is in the opposite direction, and we know that's not true. All right, what about torque? Everybody's gotten into a case where they've got a bolt that's really tight. You're trying to figure out how am I going to get that bolt loose, and you go find a bar, and you can't get it, so you what? You go find a bigger bar, right? So we have static torque, force times length. But we also have power that's being developed over an angular velocity, or omega. And that, in scientific terms, would be a radians per second scalar value. But we typically don't look at that. We want to know RPM in the machining world, right? So we look at RPM and we figure out, okay, based on the RPM and the power that we're using, how much torque are we going to develop? So we have a center of rotation. Typically, it's going to be our tool that we're most concerned about in this case. We have some radius, which is the cutter's radius, and we're applying some force as we go against that hard metal that we're trying to machine. So when we look at that, we see that the force becomes very important, as well as the diameter of the cutter. But as we're going through the material, we see the force coming down, and like I said earlier, sometimes we get misled on how far over that vector is going to be. So we have to pay attention to direction. Power, on the other hand, could be you have a 1 horsepower car. Anybody have a 1 horsepower car? Actually, that's a misnomer because I found out in doing some research, a horse actually has about 15 horsepower, just so you know. So we have James Watts to thank for the power formula, right? It's 550 pounds in a foot in 1 second. So again, that's in seconds. So you may have been looking at that formula early and going, what's 5252? It's just math. So it's 550 pounds times 60 seconds is 1 minute. That's 33,000 foot minutes. And then we divide that by 2 pi and we end up with 5252. But, so we've got James Watts to thank for that. We move on to power then. Power is going to be torque times that angular momentum, or angular velocity again. So they're both very directly related. However, as we go through these formulas and you see the arrangement's going to look the same, we rotate the tool, we have power and we have torque developed, you think, oh yeah, same, right? A lot of our customers think the same thing. They look at the power meter on the machine and they go, you know what? I've got lots more to go, right? So some factors that affect that force and therefore affect that torque level, tool edge prep. We typically look at a honed edge for cutting. Aluminum, up sharp, nice clean break, nice clean cut. Even titanium, fairly up sharp. But you have to have a stable setting in order for that to work in titanium, or else you start getting vibration and nasty things happen. So a lot of cases you'll have a honed edge. You'll have a slightly radius edge on that cutter edge. That creates more force. So we have the radius or the honed edge prep. We have coatings. Different coatings offer different coefficients of friction. They might be 0.2, might be 0.3, might be 0.4, but they vary. Angles, other than that, rake angles and things also come into play. Sometimes it's the material side. Sometimes you have more scale than you expected to have. You got to break through that extra hard surface to get down below that. Also, the cutting tool material comes into play, and this kind of loops back on itself because we've got data, and I'll show it to you here in a second, that compares high-speed steel versus an inserted carbide tool in hard metal and how much difference there is in those two. But they also have different edge preps. So that comes back, again, to the edge prep of the tool. So here's the example, high-speed steel cutter versus inserted carbide. Both 2 inches, both doing a 1/2 inch radial cut, 2 inch axial cut. 6 flutes on a high-speed steel tool, running at a slower surface footage because it is high-speed steel. 10th Alper tooth compared to an inserted cutter with 4 teeth and 225. So these are graphs. On the left side, we have the high-speed steel cutter. On the right side, we have the inserted cutter. And the blue lines are our x-axis loads, okay? So if we zoom in on that, the high-speed steel cutter is using 15% of our x-axis for that cut. What do you think the inserted end mill is using? 5%. Same MRR, 1/3 the load on the machine tool. The other thing is bending moment. And this is getting a lot of press because as we build machines stronger and bigger and the servos can take more and the spindles are bigger and they can take more, that interface, where the tool plugs into the spindle, now becomes very important because no matter what adapter you're using, no matter what tool interface you're using, everything has a limit. So if you take a tool and it's 24 inches long and you put it in the spindle and you just haul on it, you're eventually going to rip it out, no matter what connection you have. But there are connections that vary in how much they can take. So we look at this. This is all HSK. So this is HSK 6380, 125 Form A and Form B, just to kind of give you an idea of the variance. And I've got a lot more information on this that I didn't include here. But the point is, that's another factor that is not readily available to a user when they're running the machine. You need to be able to look ahead and see what's happening with that factor. All right, so here's a graphic. You got your tool, very basic shape, tool length, cutting force is being applied. Again, we don't necessarily know what that is, but it's creating that tool bending moment. Now we're back to, this is more of a static bending moment situation than a torque. But fighting that is the tool interface to the spindle and also the amount that the clamp force is being applied, because the more we pull back on the tool, the more you're securing that tool in place. So what if we don't go as far as actually ripping the tool out? Are we still okay? Depends on what you want your finish to look like. If your tool is on the edge of being pulled out too far and rotated over, you're going to see a lot of variation in your finish because now you don't have that stable, rigid seating of the tool in the spindle anymore. So it can present itself much earlier than being ripped out of the spindle. Hopefully it doesn't go that far. So what are some strategies? What if you have a low spindle power or torque situation, or you have a bending moment that's weak? So you got a small machine, small spindle, Cat 40 maybe. There's trochoidal milling, right? So the only issue here I see with trochoidal milling is this came out probably 5 or 6 years ago, really hit its apex of popularity, and it's like, oh, this is great, this is great. We had many customers that looked at that and said, wow, look at the MRR on that thing. And then they looked at the real cycle time because you're making multiple passes. And like, oh, yeah, okay, maybe the real MRR is not so great. So you got to be careful with that one too. It is very beneficial. And we use another cam system we use is Master Cam. They use dynamic milling paths, which kind of take advantage of this as well. It's also very, very productive. So there can be some alternative tool paths that you can use. The other thing is there are certain metals, like I mentioned earlier, that just love to spring back and kick your butt. So that's 13.8. We had a number of cases where we were taking very healthy cuts. They looked great until we exited. Once you exit the cut and that material snaps back, it would take out the inserts. So you've got to be careful about your entries and exits. All the cam systems have that in place. Not all the cam programmers take advantage of that. So you got to pay attention to that entry and exit stuff. Full slotting can also be an interesting case. We did a study about 2.5 years ago, and we were taking heavier and heavier radial cuts, and we were measuring the forces on our Kistler. As we passed 50%, remember the resultant force and the XY components? Some of those X components started to offset each other, and the load actually went down after we crossed 50%. So kind of a surprise there, but if you think about it, it makes sense. So if the machine can take it, meaning the tool is capable, the tool-spindle interface is capable, then you can get by with a heavier cut and in a higher radial load amount than you might think. So what are some implications? We've already talked about tool deflection and breakage. There's also high amplitude cutter vibration. If you have a little bit of vibration or an unstable cut, as we would call it, and you increase all the parameters, and now it's a more violent cut, you're just asking for damage to the machine and the tool. Also tool brands, as well as edge preps, because tool vendors make different geometries, right? So their cutting tool geometries are usually patented, usually specific. Insert geometries may be ISO standards, but they still may have different edge preps. So you got to be careful from tool brand to tool brand. And then spindle bearing radial loads also is another implication. You can exceed the bearing radial load. Here's a case. This is on our T2 where we had an arbor cutter in, and we're taking a cut, pretty heavy cut, inserted cutter, and it twisted the arbor off. Because just like I always give the analogy, you buy a new computer, they come out with software you can't run. You buy a new software, and then your computer, it's back and forth, software, hardware. You buy a bigger machine tool, then the tool doesn't work anymore because it's not strong enough. So this was a 22 millimeter pilot on an arbor, and it just sheared that pilot off. So the tool vendor and we worked together, and they've upped it, increased it now and all that. But that's the kind of stuff that you run into. As you up the game of the machine tool capability, you got to look at the tools. Can they take that load? This is an example of high amplitude vibration. So this cut started out with this was probably a straight on cut, so it spikes on entry, and then it starts to get unstable. And it goes into a state where it's regenerative. So it actually got worse and worse and worse. Now, one of two things is going to happen. You're either going to stop the machine or the tool is going to break. So one way or another, you reach the end of that graph. All right, so here's a case study. This is a comparison of different inserted mills, 3-inch diameter, all taking 20 cubes, all taking, oh, wait a minute, they're not taking the same horsepower. 16 and 20 horsepower cuts. That's interesting. And then spindle load is 45 and 55. Oh, okay. Horsepower, MRR, makes sense. But the force feedback is 70% of the load of the machine. So what happens if somebody doubles that and says, well, I'm at 45, I can go to 90% spindle power, right? Better not. So force and horsepower don't necessarily travel together. Therefore, since force doesn't, torque also does not. Next case is, this is profiling, obviously different MRR values, different cases, A, B, C, and D. Spindle load is going up, but look at the range, 25 to 48%. The force level is 105 to 144%. Now, you might say, well, is that just because the machine's, not really that strong and the radial load is too much for it, or, but here's the bending moment for that tool interface. We're at 100% when we start with 25% spindle load, horsepower. Time you get to 48% spindle load, you're at 145% of the tool bending moment at that point. All right, so the main point here is power consumption alone is not a good metric, alone, okay? Alone is the key word there. If you're looking at that spindle monitor and you're looking at that gauge or that needle or the readout, digital readout, you need to have some other ideas on how to look at the conditions that the machine is cutting under. So there are forces on the axes. You might have force feedback. You might have a graph that shows servo load. You might have radial forces on the spindle. Some of our machines, the bigger ones, have spindle feedback on forces we're applying to the spindle itself. You may want to look at torque, or you may want to look at tool bending moment as calculations that you do offline. You know, one of the things I mentioned earlier is we use Vericut. CG Tech has now this force element built into OptiPath, so that's something that you could look at. Third Wave's production module also has force feedback, so you can look at what the forces are going to be before you even put the program on the machine. And that is, in hard metals, to me, that's an important step to take. So that's pretty much it. Not sure if you have any questions or comments. But yes. So the question is, are we going to do additive on our machines? And that's a good question. As I said earlier, our R&D group that develops new machines is located in Japan, so they would make that call. We're looking, I know they're looking at it, but there's nothing that I've heard of yet that's a definite yes or no, so it's probably still being discussed at this point. Yeah.
Midwest Ultra Carbide. Did you consider also the spindle speed and the RPMs when you were evaluating the forces?
Yes. So the question is, did we consider spindle speed? So in spindle speed, again, like the formula shows, we're considering RPM. And as you're, in a lot of cases, these are integral spindles. So as the RPM goes up, the power also goes up. So these are percentages of available power at that point. So how much power is being developed and how much was being consumed. So at that particular RPM.